Okay, so let me start. We are discussing continuous functions last time, so I'll just continue from there. Okay, so just to recall, a function f is continuous at a point A. So this is something we had seen, I think, last time, that continuous at A if and only if for any sequence xn that converges to A, the sequence fxn should converge to f of A. So that's an equivalent condition. So one corollary of this would be, for example, let's say you have a function, continuous function defined on the entire real line, and let's say you know that this is 0 for all x rational. So what you know is that it is continuous at all points and that it is 0 at all rational points. Then this continuity, this condition, together with the second one here, what will that tell you about the value of the function at other points, the irrationals? So given any irrational, we know that there is a sequence of rationals such that this sequence converges to this number. And now continuity tells you that FRN would converge to F at this point X. But we are also given that all these FRNs, they are all 0 because Rn is irrational. So that means this sequence is really the constant sequence 0. So that means it converges to 0. In other words, Fx is 0. So this would imply that F is in fact 0 at every point in R, right? So continuity together with the knowledge about the values of F on a big enough subset gives you information about the function on the entire domain. So basically, this statement you can generalize a little bit. So here, the fact that this is a rational, the only role it plays is through this fact that any rational here, but more generally any real can be approximated by a sequence in this set. So for example, suppose f is defined on some interval and D is a subset of AB with the same property. That means for any x in AB, there is a sequence xn in D such that xn converges to x. And then if you know that f is continuous and f y is 0 for all y in D. So now you just look at the argument that we employed. The same reasoning would tell you that fx is 0 for all x in the interval AB. Okay. Now, when do you have this property? For any x in AB, when will there be a sequence in D that converges to X? If you recall the notion of closure of a set, so this is another way of saying that this interval AB where the function is defined, this is contained in D closure, right? Because D closure consists of all points which are limits of sequences in D. Okay, so in such a case, you say that D is dense in AB, or more generally, like there is just a definition. Suppose E is a subset of R and D is a subset of E, then D is said to be dense in E if E is contained in D closure. So if you have a function, function defined on a set E, and you know that D is a dense subset, and if continuous, sorry, I should have written that. These would tell you that fx equal to 0 for all x in E. And one application of this, for example, could be that suppose you have two continuous functions defined on some subset E. D is dense in E, and what you are also given is that these two functions coincide on D. Then they have to coincide everywhere. Why is that? Because you will simply look at the function given by this, the difference. So since f and g are both continuous on the entire set E, f minus g would be continuous, hx would be continuous. And from the given condition, you will have that this is 0 for all x in D. So by an application of the earlier statement, what you will get is that hx is 0 for all x in E, which is exactly what you want. Okay, so one application of this, I mean, part of some of the statements I'll make, I'll probably prove a little later, but just as an application, let's go back to the to this function exponential x. So this was defined, let me just recall, as a sum of this series. Okay, and what we had seen was that this function has this property. So this function is defined on the entire real line. First of all, it has this property exponential x plus y is exponential x into exponential y, and also this is x going to this is continuous. These are things we have seen already. And moreover, exponential 1, this number we had denoted by e. Okay. Now, so this is just a notation, nothing more. So this number we are going to call e. But this property, the second property, and together with this notation, so what that will tell us is that, for example, what is e square? E square is exponential 2. E square is exponential 1 into exponential 1. That is by that second property now, 1 plus 1, which is 2. And likewise, for any natural number, you will get e to the power n equal to exponential n. Okay, then you can extend it to integers. So if n is an integer, n less than 0, then what? Then you know that exponential n into exponential minus n equal to exponential 0, which is 1. That means exponential n would be 1 over exponential minus n. Minus n now is a positive integer. So this is a positive integer. That means you know that this is 1 over e to the power this positive integer. But this is nothing but e to the power n. So in fact, what you have is exponential n is e to the power n for all n integer. Okay, next take a rational. So let's say positive rational. Positive rational. Now, that second property in the previous page will tell you that if you take the product of this n times, so here n is a positive integer. N factors. So that second property, what will that tell you? That would tell you that this is exponential m by n plus m by n plus m by n. Again, n terms here, which is exponential m, which is e to the power m. So what you have is exponential m by n whole to the power n, which is the left hand side, is equal to e to the power m. That means if you take the nth root of both sides, these are all positive numbers. Just keep that in mind. So it would be e to the power m, and this is e to the power m by n. Or in other words, what you have is for a rational r, you have this equality, positive rational, and then you can extend to negative rationals just as we have done for integers. Look at the left side of the screen. So So you have these two things. Now we have already observed that the left hand side, this function is continuous. What we'll see at some point, probably today later, is the following, that x going to e to the power x, this function is also continuous. So these two functions are continuous, they coincide on the set of rationals. So now, using the property that I just mentioned earlier, it would follow that exponential x, which was defined as the sum of this series, is going to be equal to e to the power x for all x in R. Okay. Another application, so this one I'll give as an exercise. Suppose you are given a continuous function on R, and you are told, so this is the first thing that you are given, a continuous function, and 2, you are told that fx plus y equal to okay. So I'll just I'll shift it a little. I'll insert something else before this. Suppose this is continuous and you are told that show that so the first statement that I'm going to write is straightforward. So if what do you get if you put x equal to y equal to 0? This equality holds for every x and y that is given to you. So f0 would be equal to f0 into f0, which means so you just put x and y equal to 0, what you would get is this. So what does it tell you about f0?
1, 0 or 1.
0 or 1. So that's what I wanted to write in the first statement. So f0 is 0 or 1. So this is very straightforward. Still I'm writing it. Okay. So if f0 is 0, then this is going to happen, right? If f0 is 0, then you put one of them to be 0. What we will get is fx equal to fx into f0, and that would give you 0. Okay. So in the other case, what you will get is fx is for all x, fx is going to be non-zero. So fx can never be 0. Okay, because you look at fx and f of minus x, their product is going to give you 1. So they cannot be 0. Okay. 3. uh, there is a positive real such that if okay, maybe I'll just so this is essentially repeating the same argument as you have seen for the earlier case, meaning for this specific function. So the point is that you had this exponential function. What really matters in that argument is this property, the multiplicative property, that is fx plus y is fx fy. So if you are given any continuous function that satisfies that, you will have all these three, and hence exactly the same argument. Okay, this is C, this is not E. So this C could be some other, some real. Okay, now the other exercise which I started writing down earlier. So here I've just changed the relation slightly, this equality. So now it's additivity, fx plus y is fx plus fy. Then show that fx equal to, show that there is a real such that this equal to this for all real x. So again, it would be an application of the first result that we have seen today. So you first see what happens at positive integers, then you see what happens for negative integers, meaning all integers. Then you see what happens for rationals, and then you extend by continuity to all reals. So that those would be the steps. Okay, now let me go back to the type of properties we started proving last time. So we had looked at two properties last time, basically. One was sign preserving property, and the other one was intermediate value theorem. Okay, by the way, so do you have any questions or anything you want to ask here from this part? Any doubt or any clarification that you want to ask? Okay. So what did these two properties tell us? Sign preserving property was that if f is defined and continuous on an interval, c is some point in this interval, and if c is, let's say, non-zero, so either positive or negative, then the sign preserving property tells us that there would be an open neighborhood around C where fx will have the same sign as this fc. And the argument is that you will choose an epsilon small enough so that fc minus epsilon and fc plus epsilon, this interval would exclude zero. which you can do. Whether FC is negative or whether FC is positive, you can choose a small enough epsilon so that that happens, it excludes 0. And then corresponding to that epsilon, you choose a delta corresponding to that epsilon and use just the definition of continuity. That tells you that within this interval, fx would stay away from 0. So the sign is preserved in a small enough interval. That's sign preserving property. And what does intermediate value theorem tell us? If f is continuous on a closed interval like this, a closed bounded interval, and if a and let's say you have a real which lies between the two numbers fa and fb, the values at the two endpoints, there could be equality also. Or the inequality could be in the other direction. So fb could be the smaller of the two and d could be between them. Even then the same conclusion. The conclusion is that there would be some c. This c could be one of the endpoints also. Fc is going to be equal to d. So any intermediate value is attained. That's what it says, intermediate value theorem. And if you keep strict inequalities here, if you just have less than at both places, then there would be a c in the interior, that is in the open interval, it would be. So those are the two properties that we saw last time. Okay, so next property, let's say again f is defined on a closed bounded interval. Assume that f is continuous. So continuous on the closed interval. That means for the endpoints, this I mentioned last time. So for a, it would mean that fa equal to limit fx as x goes to a from the right. For b, it would mean that fb equal to limit fx as x goes to b from the left. Okay. Then there are reals, small m and capital M, such that fx lies between these two numbers. Or in other words, f is bounded in this interval. If it's a closed bounded interval, f is defined on and is continuous there, then f has to be bounded there. Okay, and I mean, the alternate ways of saying the same thing, that this set is bounded. This is the range of f that is bounded. So a continuous function defined on a closed bounded interval would be bounded. So first of all, for this statement to be, for the conclusion to be true, the continuity is something that is important. Otherwise, this is not going to be true. So for example, take the function fx equal to, let's say your interval is 0 to 1. You take the following function. You define fx to be 1 over x if x is different from 0 in this interval. And at 0, you just define it to be something, let's say, this way. So if you look at the range of this function, this is not going to be bounded. So this is the function. At 0, you have defined it to be 0, but at points close to 0, it blows up. So you can check that this function is not bounded. You can take x small enough, for example, x to be of the form 1 over n, and then fx is going to give you n. So you can make fx as large as you want. So it's not bounded above in this example. Similarly, on the other side also, like bounded below, you want to construct an example, take -1 to 1. Essentially, you can use the same function. So you define fx to be 1 over x if x belongs to -1 to 1 except the point 0. You define it to be 0 if x is 0. So then it would look like the graph. So by taking the point very close to 0 on this side, you can make it very large on the positive side. Taking your point very close to 0 on the negative side, you can make it very large on the negative side. So this will not be bounded, neither bounded below nor bounded above. So for the statement, continuity is something very, very important. Okay, now how do we prove it? So let's prove, so there are two parts. There exists small m such that this happens for all x, and there exists a capital M such that this happens for all x. So let's prove those separately. Okay. So basically there are two statements to prove. E, the range, that is the range of f, is bounded below and bounded above. These are the two things to show. So let's assume that is not bounded below. Okay, then what does it mean? That means that given any real m, there is an x in the domain. The domain in this case is this interval, such that fx is less than m, right? Okay. So let's take m equal to -1. Take the corresponding x. I mean, take one such x. So choose x1 such that fx1 is less than -1. Next, you look at -2. Again, this statement will tell you that there is an x where fx is less than -2. So call it x2. So fx2 less than -2. So this way you can keep producing xn's in this interval such that fxn is less than -n. Okay. Now the domain is this closed interval a to b. The xn's are all here. Maybe x1 is this, x2 is this, x3 is this, etc. But they're all in this bounded interval. So xn is a bounded sequence. What does Bolzano-Weierstrass theorem tell us?
There exists a converging subsequence.
There is a convergent subsequence. So Bolzano-Weierstrass. It has a convergent subsequence. So let's say this is that subsequence. Now this subsequence, all its terms are in this closed set A to B. So where will this x lie? X will lie again in this interval, because this interval is a closed set. You have a sequence from this closed set that converges. So the limit of that sequence must lie in that closed set. So x is again here. And what does continuity tell you? Continuity tells you that you must have, so since this sequence converges to this number x and f is continuous throughout this closed interval, this sequence must converge to fx. Okay. But on the other hand, what do you know about this? You know that this is less than minus kn, and kn is a subsequence of naturals 1, 2, 3, 4, etc. So this is less than minus n. So these two will contradict each other. So this is not bounded, the fxn sequence. So on one hand, it must converge to this real. On the other hand, this is not a bounded sequence. So they contradict each other. So your initial assumption that E is not bounded below, that leads you to something contradictory. Leads you to a conclusion that's contradictory. That means this cannot be correct. So this must be false. So that tells you that fx x bounded below. So exactly similar argument would tell you that this is bounded above. Okay. So any questions from here? Okay. So continuous function on a closed bounded interval is bounded. That's what we have just now seen. Now next, let's look at this this set, the range of f. So now we know that this is bounded above and bounded below both. So we can talk about the supremum and the infimum. And when I say we can talk about, what I mean is that this is real, this is also a real. It's bounded above, so the supremum is not plus infinity, it is a real number. It is bounded below, so the infimum is again a real, it's not minus infinity. So now let us just call this number m, capital M, and this number small m. Okay. Now let's look at this first. So M is the supremum of a set. That means what? If I look at, let's say, m minus 1 over n is some natural, non-zero natural, 1, 2, 3, etc. So this is no more an upper bound. That means so I'll just write this here. For each n, this is no more an upper bound. That means there would exist an xn here such that fxn is bigger than this. But of course, the entire set is bounded above by m, capital M. So these are all less than equal to m automatically. So this part we already have. The stress is here on this first inequality. Okay, so we have this. Then what can we say about this sequence fxn? The inequality that they satisfy is, again, let me write down on this page. So what can we say about this sequence from this? As small n goes to infinity, this goes to capital M. On the right hand side, you have a constant sequence which trivially goes to capital M. So the one in the middle, that has to converge, and that has to converge to M. So this converges to M. But once again, all these x1, x2, etc., they're all lying sitting between A and B in this closed interval. So once again, xn has a convergent subsequence kn that converges to some x. So this part is exactly same as what we argued in the earlier case. So this means that this point x has to come from the same closed interval a to b. And by continuity, what do you get? Continuity tells you that fxkn this must converge to f of x. Okay. Now, the sequence fxn itself converges to m, and this is a subsequence of that. So we also know that this actually converges to capital M. Now you put this and this together. What that tells you is that fx must be equal to m, capital M. Or in other words, there is a point x in A to B such that fx is the supremum. So the supremum of the range that is actually attained for a continuous function on a closed bounded interval. So if you look at the range would be the values, fx values. So in this picture, at least, supremum is this point, infimum is this point. So what we have argued is basically this supremum would be attained at some point here, and a similar, exactly similar argument would tell you that there would be a y so both this small m and capital M would be attained in this interval. So first we saw that if we have a continuous function on a closed bounded interval, the function has to be bounded, the range has to be bounded. And then we saw that the supremum of that range, infimum of that range, those are in fact in the range. So there are points where those values are actually attained. And now you combine it with intermediate value theorem. So what you get is that the minimum value, the infimum, that would be attained at some point y. The supremum, which is capital M, is attained at some point x. I mean, y could be, in this picture, y is less than x, but y could be bigger than x also. Now, let's just go with this diagram. So y is less than x. Now, if you look at the interval y to x, this is obviously sitting inside the initial interval that we started with. Okay, here, what are the values at the endpoint? Small m and capital M. So you employ intermediate value theorem here. So if you have some d between these two, small m and capital M, so there would be a point between y and x where that value would be attained. So anything here, d between capital M and small m, there would be a point between y and x where okay, but this z is of course is in the initial interval also. So what it tells you is that if you take any d between the supremum and the infimum, that d would be attained somewhere in this interval a to b. So first, the function is bounded. Second, both supremum and infimum are attained at some points in the interval. Third, anything between the two numbers, supremum and infimum, that is also attained somewhere in the interval. Okay, so any questions? Okay, so let me write down an exercise. Give examples of functions defined on a closed bounded interval such that, so three different examples. Okay, let me first see how many statements I'm going to write. F is not bounded. This such an example you have already seen, but you can try to construct further examples. F is not bounded. F is bounded, but closed bounded interval A to B, such that this is not attained in A to B. Okay, which means that there does not exist X in here in this interval such that Fx equal to the supremum of this thing, which is the range. Three, analogous statement for infimum. So if bounded, but there does not exist X such that Fx is infimum of range of F. I'm not going to write this anymore. Range of F.
Here we don't have to say, here we don't have to have continuity, right?
Right. Because we already know that if we have continuity, then all these things, cannot hold because we have proved to the contrary. Right?
Yeah. Yes, sir.
Yes. So examples of functions. So these have to be non-continuous. Okay, so these three. So three examples. At least three examples. At least one of each type. Okay. Okay, let me write this as an exercise. Suppose F is defined on a closed bounded interval. So here I'm not imposing any condition. So it need not be continuous, need not be anything, just a function which is defined on the whole interval. Show the following. This quantity equal to, so first of all, what does this quantity basically mean? That you are looking at all possible values, meaning you are taking pairs of points and looking at the values at those 2 points and looking at their difference. And then you are looking at the supremum. So this is a function. So suppose you draw a graph. It may not be continuous. I'll just draw something continuous. So for example, here, if you look at this point, if you look at this point, you look at their difference, that should be the supremum in this picture. Now, just to kind of illustrate what this quantity may refer to, the function may not be nice, so there may not be points where the supremum is attained, points where the infimum is attained, etc. So all those things are there. So you are looking at differences between values at 2 points, and then you are looking at the supremum of these differences. This is going to be equal to infimum of same thing, and which is also equal to, so this is almost like this expression, so just remove the modulus sign here. I mean, since we are, so these two sets are different, this set and this set, they're different, but since we are taking supremum, this removing the modulus will not matter. So try and prove this these two equalities. So this first and the third, that is essentially this statement. So this has nothing to do with the range of a function. It's like this. Suppose you have a subset of R which has this property that whenever x belongs to E, minus x also belongs to E. So it's symmetric about the point 0. Any point, any real belongs there, its negative also belongs there. Okay, and then the supremum of E is same as supremum of if you just look at one side of the set, because this set is then just the positive side of that set. And when you look at the supremum, it really does not matter whether you're looking at the entire set or just the positive side of that set, if it is symmetric. So this first and the third quantity, equality between them is basically because of this. That this set is symmetric, there this will come into picture, because negative of this would be fy minus fx, which is again of the same form, fy minus fx, where y and x are there. So this is symmetric, so first and the third are equal, and then you show equality between these two. Okay, now the next property. So again, let's say f is defined on a closed bounded interval, and also this is continuous. And let's say epsilon is something that is given to you. Then what this property tells you is that you can divide this interval a to b into very small subintervals, so that over any of these subintervals, f cannot vary by more than epsilon. So, okay, just going back to the previous page. So this quantity, let's use some notation for this quantity. So this basically tells you how much f can vary within this interval a to b. The supremum of f in this interval minus the infimum of f in this interval. So that's the maximum f can vary within this interval. So fx minus fy cannot be any bigger than this. So what notation to use? Oscillation of f in this subinterval.
Sir,
Okay. Yeah.
so in this last exercise question, we are not assuming f is continuous, right?
Here in this exercise on the right hand side.
Yeah.
Yeah. No assumption on f at all.
Okay.
Just that f is something function defined on the entire interval. That's all. Okay. Now here, so what we are going to prove is this, that so here we are given a continuous function on this closed boundary interval, and also epsilon is given to us, some positive real. Then there is a partition so partition means just this, that you have points in between, so that you have a so you split this closed interval into smaller subintervals whose union is going to give you this entire interval, and who will intersect only at their endpoints. There is such a partition such that, so over each subinterval, the oscillation, the maximum variation can be at most epsilon. So and this is again, so fx, the supremum over this subinterval minus the infimum over this subinterval. Okay. So this result, the name is not so standard perhaps, but it's a suggestive name, so it's good to small span theorem, you can call it. So basically you can divide the interval into small subintervals so that the span or the oscillation of f over each subinterval is small.
And so the number of intervals would depend upon the value of epsilon.
Right. Yes.
Okay.
So this n is going to depend on epsilon, but that is okay. It can be very large if epsilon is very small, which is fine. Okay. So how to prove this? So let's say that this statement is not true. So this is the statement that if f is a continuous function and epsilon is any real, then there is a partition like this such that this happens. Now, this does not hold. What does that mean? So for every epsilon positive, something happens. So the negation would be that there exists an epsilon positive for which there does not exist any such partition, right? Such that, so I'm not writing the entire thing again. So the statement says that for every epsilon, there should exist a partition such that whatever that follows happens. So the negation is that there is an epsilon positive for which there's no partition such that that condition is true. Okay, now let's see. So this A to B, this entire interval does not admit a partition for which that quantity, not this, sorry, xi plus 1 less than epsilon for each I. Okay, so that means suppose you look at the endpoint. So suppose this admits a partition such that this happens, and this interval also admits a partition such that this happens. Then if you put the two together, you will get a partition of the entire interval such that this would be true, right? So if it fails for the entire interval, then it has to fail for one of these subintervals, or it has to fail for both, right? So either a to a plus b by 2 does not admit a partition such that or does not admit a partition such that this happens. Because if both admit partitions,
Sir, I did not understand this point.
okay, I'll just repeat. So suppose you have a partition here. Let's say this is x naught x1, etc. Let's say xm minus 1, and this is xm. Suppose you have a partition here such that over each subinterval, the maximum variation is epsilon. Okay.
Okay.
Also, assume that you have another partition for this, the interval on the right side, this. So now you call this y0, this y1, etc. yk minus 1, and this is yk, such that here also over each subinterval, the maximum variation, maximum oscillation, that is less than epsilon.
Okay.
Okay. Now you put them together. So you have this x0, x1 up to xm, which is equal to y0, then y1, y2, yk, which is b. So what you get is a partition for the entire interval a to b. Right?
Yeah. Yeah.
Now, for this partition, any subinterval you look at, there the oscillation is at most epsilon.
Any subinterval of length a plus b by 2.
We are not getting into the length of the subintervals. Just any, okay, by subinterval, I mean these smallest ones. When we are talking about a partition, what we are doing is we are choosing a strictly increasing string of numbers from that interval.
Okay.
And when I say subinterval, I just mean the smallest ones here, not, for example, x1 to x5. No, these ones.
Okay, sir. Yeah. Understood.
Yeah. So now coming back to the left side, this picture. So if I have a partition here where each subinterval has the property that this partition has the property that over each subinterval, the maximum oscillation is less than epsilon. And here also you have a partition which has the same property, that is over each subinterval, the maximum oscillation is at most epsilon. When you look at this partition, this is a partition of the entire interval a to b. Okay. Now, for this partition, any subinterval is either from a y subinterval or an x subinterval, right?
Yes, sir.
And over each, the oscillation is at most epsilon.
Okay, sir. Yeah.
Yeah. So the interval a to b admits one such partition. But what we have assumed is that the statement does not hold. That means the interval does not admit any such partition.
Okay, sir. Yeah.
Right. That means that one of these subintervals will not admit any such partition.
Yes, sir. Yeah.
Yeah. Okay. So to begin with, we know that this interval does not admit a partition such that that condition holds. Now we have concluded that we have a smaller subinterval which is exactly half the length. So this is either a to a plus b by 2. It's just like in the proof of Bolzano-Weierstrass theorem, or this interval. And if both of them, neither of them admits partition, then you just, you just stick to a fixed convention. Let's say we'll take the left subinterval in that case. So you get a smaller interval of half the length, which has the same property. It does not admit a partition satisfying that property. Now you repeat the argument for this. So now this is your new interval. You know that this does not admit a partition such that over each subinterval, the oscillation is at most epsilon, which means either this will not admit a partition such that it happens, or this will not admit a partition such that that thing holds. If both of them admit a partition such that over each subinterval the oscillation would be at most epsilon, the entire interval would admit a partition. Putting them together, that would give you the partition. So at the next stage, you will get A2B2, which is again exactly half the length of the previous one, which does not admit a partition, and so on. So again, like in the proof of Bolzano-Weierstrass theorem, what you have is this. You have A0, A1 I missed, A1, A0, A3, etc. increasing sequence, and then B3, B2, B1, B0, B0 is B, and A0 is A. So we have an increasing sequence of the left endpoints, decreasing sequence of the right endpoints. Bn minus An is B minus A by 2 to the power n. Okay, and for each A and Bn, you have this property that A and Bn does not admit any partition this will also depend on n, but I'm not writing that. This is Bn such that oscillation of f over okay. Now let's look at this sequence An. This we already know that Ans are all bounded above by the right endpoint B. It's an increasing sequence, so An increases to something. Bn's decrease, they're all bounded below by the left endpoint, which is A. So Bn's decrease to again something. And because of this this condition, so this is exactly like in the earlier case. Sorry, this is, what you will get is that C equal to D. So normally each An is less than equal to Bn, so C would be less than equal to D. Because of that length condition, what you will get is actually C equal to D. C cannot be strictly less than D. So A0, A1, A2, etc. they're going to C. B0, B1, B2, etc. they are going to D. If this is positive, then you will have a problem if you take n large enough, because all the Ans are here on this side, Bns are on this side. An minus Bn has to be bigger than this positive quantity. But now by choosing n big enough, you can contradict that. So that was the idea here. Okay, so Ans and Bns, they converge to the same number, and this number is in the closed interval C, A to B, which means that f is continuous at this point C. The C is there. Okay. So now let's say this C is in the interior. C could be one of the endpoints also. Let's look at just this case. Okay. Now, at C, f is continuous. So now what you do is you use continuity. So this epsilon is with you from the beginning. You have assumed that the statement of the theorem is false. So there exists some epsilon. So it is that epsilon that you are still working with. Okay. Now what you do is you look at fc minus epsilon by 2, fc plus epsilon by 2. Okay, and use continuity at C. So that would give you a delta such that between C minus delta and C plus delta, so there is a delta positive such that x belongs to C minus delta, C plus delta would imply fx is between fc minus epsilon by 2 and fc plus epsilon by 2. Okay, so this entire interval fx will lie between these two. Okay, so what does this tell you about the oscillation in this interval? The supremum of fx in this interval minus the infimum of fx in this interval. That can be at most epsilon. If fx lies here, the supremum of fx can be this at most. Infimum of fx can be at has to be at least this. So what would be the difference? The difference can be at most epsilon, right? In fact, let's do one thing. Instead of epsilon by 2, let's choose delta corresponding to epsilon by 3, so that there's no confusion regarding strict inequality, etc. Okay, so let's do this. Epsilon by 3, epsilon by 3. So then in this entire interval, so this is fc plus epsilon by 3. This is fc minus epsilon by 3. So what is the maximum oscillation possible? Maximum oscillation possible would be 2 epsilon by 3, right? Okay. Now look at this C minus delta and C plus delta. I'm just drawing again because it's a little bigger so that I can put more things inside. Now, for a large enough n, you will have this an between C minus delta and C and bn between C and C plus delta. Now, what was a and bn? A and bn, we saw that it is an interval that does not admit any partition such that on the subdivisions of that partition, the oscillation is at most epsilon. It does not admit any such partition. But on the other hand, here you have a slightly bigger interval where a and bn is completely contained. That means you just look at oscillation of f a and bn. It can be at most 2 epsilon by 3 because this a and bn is closed. This is contained in C minus delta to C plus delta. So the oscillation over this entire interval is in fact less than equal to 2 epsilon by 3, which is strictly less than epsilon. So in fact, this itself is a partition for which this condition holds. So this contradicts your choice of A and Bn. The way you chose A and Bn at each stage, that is being contradicted. So at each stage, what you are doing is you are choosing a subinterval a and bn which does not admit any partition, for which over each subdivision the oscillation is small. But now, looking at the two sequences a and bn, you have reached a point C, a single point C. Now you are using continuity of f at that point C to get a small neighborhood around C where the oscillation would be small. And now you are taking a large enough n so that the entire interval a and bn fits inside this neighborhood of C. So the oscillation over the entire interval a and bn is in fact small, so which contradicts your choice of a and bn earlier. So it's possible that you're not convinced about everything yet. So what you should do is you should go back and try to go over the entire argument, and by go over I mean you just try to reconstruct the entire argument yourself, and you can discuss with others. So this is the time when you are allowed, in fact I would say, you should discuss with others so that your doubts etc basically gets eliminated. So you do that, go over this argument, try to reconstruct, and then if you have any doubt, so you can go over this argument once more, or you can write through the course page and we can discuss there also. So before you stop, so what was the statement? That is the important thing ultimately. So because you have to use these statements later to either solve problems or to prove something else that comes up later. So what this result says is that if you have a continuous function on a closed bounded interval and you are given a very small number, epsilon positive, then it is possible to divide this interval into very small subdivisions such that over each subinterval, the maximum variation or the oscillation is within epsilon, can be at most epsilon. So within each, the variation won't be much. The function can vary a lot within this interval, though we have seen that if it's continuous, it has to be bounded. So it cannot be, for example, infinity, but it can be large. But then, given epsilon, we can choose small, partitions with very small subdivisions, so that within each the variation is not much smaller than epsilon. So this would be especially useful when we come to integration. Okay, so I think I'll stop here, or maybe just give me 2 or 3 minutes. I'll just I'll introduce a small definition and then stop. Okay, so let's recall the definition of continuity of f at a point A. What was the definition? And if you state it in terms of epsilon, etc., given epsilon positive, there is a delta positive such that whenever x is within delta distance of a, fx is within epsilon distance of fa. So here this delta, it depends on epsilon and it also depends on a. This is something I had mentioned at the beginning when I think either when I define limit or when I define continuity with the help of this function. I think I had pointed out that this delta would depend on not only on epsilon but also at which point you are close to. So this now, even if let's say f is continuous throughout some interval, open or closed does not matter, some set, even if f is continuous at every point, when you go to each individual point and try to choose a delta, etc., there it would depend on that particular point as well as this epsilon. If the choice of delta does not depend on the point but only on epsilon, then, so this is not exactly a precise definition. I'll write down the precise definition probably next time. But this is basically the main idea behind the definition. So if the choice of delta does not depend on the point but only on epsilon, then you say that f is uniformly continuous over that set. Then one says that f is uniformly continuous on its domain. Okay, so I'll start with this. So this is almost precise, but I'll just write down a slightly more precise statement. So that is uniform continuity. And what this small span theorem will tell us is that any function that is continuous on a closed bounded interval is uniformly continuous. So we'll see that next time. Okay, so that's where I'll stop. Any questions? If not, so let me disconnect. We'll see you day after tomorrow.
Thank you, sir.